Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. This is the second video on chapter 11, in which we will prove Brion's theorem. Let me remind you of one of the videos for chapter 2, where we discussed formal Laurent series. We realized that formal Laurent series do not form a ring, but a module over Laurent polynomials. And back then, we had a map from a subset of formal Laurent series, namely the ones that naturally map to rational functions. And we realized that this was a module homomorphism, because I can also think of the rational functions as a module over the ring of Laurent polynomials. And we realized back then, so this was sort of a one variable version of what's to come here, we realized that this variant of the geometric series where we sum z to the k over all integers k gets mapped to the rational function 0 under these considerations. This should remind you of the previous video where we discussed Brion's theorem in one dimension. And if you unravel this, you can think of this formal Laurent series z to the k over all integers k as the integer point transform of the real line. And again, looking back to what we did in the previous video, you should convince yourself that this should correspond to the rational function equal to 0. Compared to chapter 2, we now know a lot more about integer point transforms, and we now consider the set CL sub D. These are all formal Laurent series that are integer point transforms of rational cones. And I want to consider all cones living in some d-dimensional space. By the way, these are cones in the sense of the previous video, in the sense that there are intersections of half spaces whose corresponding hyperplanes meet in a point. And rational just means I can describe these half spaces or these hyperplanes with inequalities or equations with integer coefficients. Going back to chapter 2 one more time, we here considered all formal Laurent series, albeit in one variable, that sort of naturally correspond to rational functions. And this should make some sense now, because we know the integer point transform of a rational cone evaluates to a rational function. Strictly speaking, we have to be a little careful. So we've proved that simplicial rational cones naturally evaluates to rational functions. And then general rational cones can be triangulated using simplicial cones. And so we can write the integer point transform, for example, using inclusion-exclusion. But it's not quite clear if I write such an integer point transform in two different ways, as a sum of rational functions coming from simplicial cones, that the result is well defined. And this lemma here, lemma 11.1, is supposed to clear the situation. It says that there's a unique linear map from this subset of formal Laurent series, namely the ones corresponding to integer point transforms for rational cones in some dimension d, to rational functions in d variables, with the property that if we have a simplicial cone, so we know we can always write a simplicial cone in this form where the w's are linearly independent. This gets mapped to the rational function that we've encountered in chapter 3, where the numerator is the integer point transform of the fundamental parallelepiped, and the denominator is determined by the generators. When I say linear map here, I mean a modular homomorphism, because again, I can think of my Formel-Laurent series corresponding to rational cones as a module over the ring of Laurent polynomials. And of course, the ring of rational functions is again a module of Laurent polynomials. Now everything happens in D variables. Let me give you an idea why this lemma is true. If we have a simplicial cone, then both the numerator and the denominator that you see over here are well defined. And so what we'll do is we'll map the simplicial cone to this rational function. And then we extend this map linearly using triangulations. One reason why lemma 11.1 is useful is because we can now make precise, at least within the subset of Formel-Laurent series belonging to rational cones, which of those map to 0. So I claim the rational cones that are not pointed, in other words, the cones that contain a line, map to 0. You've seen the one-dimensional version in chapter 2. In one dimension, containing a line means you're the whole line. And indeed, that corresponding Formel-Laurent series map to the rational function 0. And in some sense, the proof of this lemma goes actually the same way as what we did in chapter 2. If K contains a line, then let's say we parameterize this line as V plus some lambda times W. In other words, W is a direction vector for our line. And what this means is that we can shift K by W and nothing happens. And of course, this means that we have an identity of the integer point transforms, namely sigma of K plus W is the same as sigma sub K. I guess I'm assuming that this line is a rational line, so W is some integer vector. And that means I can write my sigma sub K plus W as Z to the W times sigma K. And what follows from here is that you have a product that gives you 0. And now what I do is I apply the map phi on both sides. Phi is a linear map, so it's a modular homomorphism, and this factor over here is in the module. This is a Laurent polynomial. And in the ring of rational functions, this is non-zero. So in fact, in the ring of rational functions is a field. There's no non-trivial zero divisors. And that means that whatever the image is over here under the map phi has to go to 0. Here's why we really need this lemma. I want to remind you that we introduced tangent cones in the previous video. So you start with a polytope, take a face, and then the tangent cone is sort of the minimal cone with apex your face that contains the polytope. Back then, we already remarked that the only tangent cones that are pointed are the vertex cones. It's the case when your face is a vertex. In other words, if you have a tangent cone of a face that is not a vertex, this contains a line, and so the map in lemma 11.1 maps the corresponding integer point transform to 0. This, in turn, is important for Brion's theorem. And here we use another ingredient from the previous video, namely the Brion-Gram theorem. Let me tell you what happens in the case of a simplex with Brion's theorem. What we'll do now is we apply the Brion-Gram theorem, I'm reminding you here of its statement, to integer point transforms. What we're saying is, since we have this identity of indicator functions, we can specialize this in the land of formal Laurent series to integer point transforms. So on the left-hand side, we get the integer point transform of delta. And on the right, we get this sort of alternating sum of integer point transforms of tangent cones. And if I now apply the map phi, we just saw that all these tangent cones have integer point transforms that map to the 0 function, except for the vertices. And this gives the simplicial form of Brion's theorem. It says that I can write the integer point transform as a sum of the integer point transforms of the vertex cones. To get the general statement, we play the same trick as what we've done in chapter 3 and 4. We triangulate a polytope and then shift sort of the bounding hyperplanes of the polytope and the triangulation in such a way that none of them contain an integer lattice point, but we still get the same integer point transforms. We outline the details in section 11.4, but in essence you get Brion's theorem in the general case from the simplicial version, because in a triangulation the vertex cones sort of add up as set functions. And so if you do this smartly, the integer point transforms of the vertex cones of the simplices in a triangulation, they add up nicely to integer point transforms of the vertices of the polytope. Let me finish this video with the remark that started the previous video. Just like in this one-dimensional case, the general statement of Brion's theorem says that you can get a finite Laurent polynomial, namely the one corresponding to your initial polytope, as a sum of integer point transforms belonging to infinite cones, namely the vertex cones of your polytope. So I hope you agree this is somewhat of a magic statement. So over here we have a finite object P. So this is a Laurent polynomial. And the objects on the right and the sum over here are integer point transforms of the vertex cones. These are very much infinite objects. But remember, we had to apply this map phi, otherwise we would have more tangent cones here. At any rate, these are now rational functions. And not only do they somehow represent these infinite objects, these cones, but somehow the rational functions, when you add them up, they cancel just right to give you, in the sum, the finite integer point transforms, the Laurent polynomial that belongs to P.